right, guys, so what we're covering today is 2-6. Now, hopefully you've been working on the assignment so far this week that we've covered. And I would say specifically with 2-6, do not wait till Sunday almost at midnight to try to get this done. It is 20 questions. Now, most of what we're covering in 2-6 is going to be with graphing the functions. And we're going to specifically talk about graphing parabolas, absolute values, cubics, and radicals first, especially with graphing in this program here. Because if we're going to graph a parabola, we need 5 points. And especially in the graphing, or in the ALEX, you're going to need 5 points to be able to graph it. And as you've seen so far, we can plot points, especially when we're dealing with circles, which was 2-3, I believe, or 2-2. I think, yeah, 2-2. What we covered on Monday, you saw the ability to plot a point. You can plot the 2 points and do that there. With quadratics, you're going to plot the 5 points. It has a button for quadratics. You hit it, it'll graph it. But you need the 5 points plotted. Now, the 5 points that we pick, one of them is going to be the vertex, which is the highest or lowest point on the graph. And then you're going to pick 2 points to the left and right. And it will say in the instructions for each of the parabolas that you need 5 points, you need the vertex, and 2 points to the right and 2 points to the left, going from there. Now the vertex, if it's given to you in standard form, or in vertex form, the vertex is the point h, comma, k. And the h value that we pull out of the parentheses, we really flip the sign. So if h is positive, it's going to look like x minus 4. 4 is our positive h value. If it's negative 4, inside the parentheses, we're going to have x plus 4. Inside the parentheses is the opposite sign. The number outside the parentheses is going to be exactly as it is. So once we get this point, we're going to pick 2 spots to the left and right of it. So if h was 4, we have an x value of 4, then we do 5, 6, and 3, 2. 2 x values either side. And then we just find the y values that correspond with them. Now if it's in standard form, it's in a different color. So we're talking about ax squared plus bx plus c is our function. The vertex is given to us by negative b over 2a, comma, f of negative b over 2a. Now the negative b over 2a, we kind of get that. It's just going to be negative, whatever our b value is, over 2 times a. So we plug that information in and get that. Now f of negative b over 2a is just taking whatever that number is and plugging it into the function to see what it is. And again, just like with our other one, then we take 2 spots to the left and right and plot those points. Questions on this here? Now with most quadratics, you can use the graphing calculator. Since we have the TI-84s, y'all have a TI-84 that you can use. You can plug it in. Now you can use this information here to find where the vertex is, or looking at the graph where the lowest spot is, and go from there. Cubics, radicals, and absolute values. Now the cubics, most every single cubic I saw there, they're not going to get too in depth with them. They're really going to say they need 5 points at least. And in the instructions, it tells you that start off with x is 0 and then go 2 points to the left and right. Start out with x is 0 and then go 2 points left and right and find those. And really what they're saying with 2 points left and right, with any of them, even the quadratics, x, y, negative 2, negative 1, 0, 1, 2. Plug those x values into the function, see what the y values are, plot those points, and use the cubic or same type button that you'd use for quadratics to graph it. Cubics aren't too bad, especially if we're not getting too complicated with it. Questions on this so far? Okay. Radicals. The main ones we'll be looking at are the square root of x. Now with this here, what is the one number, what kind of numbers do we know that can't not be inside the radical? They cannot be less than 0, right? Because if they're negative, we can't take square root of them. Now with graphing radicals, one of the main things you're going to look for, the first point is what's going to make whatever's inside the radical be 0. Whatever's inside the radical is 0, because that's the first point on the graph that does show up. So if we had the square root of x minus 2, I can set x minus 2 equals 0, which just tells me that the first x value that we could possibly have is 2. And that's going to be my first spot. Now from there, depending on the function for this here, we can start off with x is 2, 3, 4, going on that way, and get multiple points going from there. Now, luckily enough, I have tested it with the ALEX program. You can put radicals in for your plotting points. So for like 3 minus 2 is 1. Square root of 1 is 1. That works fine because it's a perfect square. Because this is actually 0, this would be 1. Now the next one, 4 minus 2 is 2. Square root of 2 is not a nice number, but ALEX will let you plot the point for square root of 2 as the point itself. It will let you do that. You don't have to give it a nice number or a decimal number. It will let you do those. Does that make sense? Now, if you wanted to, especially if I was doing this by hand, I pick certain spots particularly, certain x values in particular, because we know that 1 is a perfect square. The next perfect square after that is 4, yes? Well, what number minus 2 would give us 4? What minus 2 is 4? 6. So instead of doing 4, 2, I would do 6. Because 6 minus 2 is 4. Square root of 4 is 2. We get a nice number. Does that make sense? Because with certain ones, with graphing these, if I graphed it by hand, I would start picking x values that would give me a nice square root to simplify. Because the next nice square root after 4 is 9, because we can take the square root of 9. Well, I know I'm minusing 2, so I'd pick an x value of 11. Because 11 minus 2 is 9. I can take the square root of 9, and it works out nicely. Y'all see that there? So it's almost, especially with radicals, I start trying to see what numbers I can plug into x minus 2 or what's inside the radical that simplifies to a perfect square, if we were trying to do this by hand. But again, even with radicals, y equals, clear that out, I can say second square root of x minus 2. Graph. We have this here. I can look at the table. Well, at 2, that's our first number that works. Then I have points going on from that. And we see at 3, we get 1. 4, we don't get a nice number. 5, we don't. At 6, we have 2. 7's not nice. 8's not nice. 9 isn't. 10. 11. We have another nice number because 11 minus 2 is 9. We can take that square root. Questions on these here? It needs at least 3. It's either 3 or 4, and again, the directions will specify how many you need for it. 5 is, you can use 5 for this here. That works out nicely too. And absolute values, you need 3 points. And with absolute values, you're going to have to use the ray feature. And the ray is just a point and you pick a point going on from there. And you always start with kind of the vertex or the spot, the lowest or highest point of the V. Now with absolute values, you can still graph these, because our math over 1 does give us the absolute value. We can say x minus 1. And it'll give us the graph. So 1, 0 is the lowest point on it. We would graph it, and then select the point to the left and select the point to the right. So 1, 0 is the lowest. I would click it to start as the endpoint, then go over to 0, 1, hit it. I would have half of it. Do it again, but go the other direction, and we'd get the other half. Does this kind of make sense for these here? Now, one thing I didn't say with quadratics, x, y, 1, 2, vertex, 1, 2, here. The y values to either side of the vertex are going to be the same. That's just how quadratics work. Because at the vertex, the line that goes through the vertex is also called the axis of symmetry, and everything's mirrored across it. So really, once you find these, if you have this y value, you have this one. And if you have this one, you will also have that one. They will mirror each other. And we'll see that here when we start looking at some of them. Any questions on any of these here? Still good with these so far? Yes? Now, specifically, we're going to talk about the transformations first. And there's a few. The easier, what we call rigid transformations, move the function up, down, left, right. They do not change the size or shape of the function. If we have something added to the function or subtracted from it on the outside, it's moving it up or it's moving it down. So if we have x squared minus 4, it's moving the function x squared down 4 units. We're subtracting 4 from it. Or if we have x squared plus 7, we're moving the whole function up 7 units. We're not changing the shape or what it looks like. We're just moving the whole thing up or the whole thing down. And that works with any of them. The cubed root, or the square root of x plus 1, just means I'm taking the whole square root function and moving it up 1. Or if we said minus 1, we'd move the whole thing down 1. So if we're looking at this here, now what I just drew is the absolute value function, absolute value of x. This is the parent function. Because if we're looking at, so for A, the absolute value of x minus 3. Okay. Absolute value of x minus 3. All we're saying, group those together, is that we're taking this function and moving it down 3 units. That's it. That's all the x, or the minus 3, is telling us. Let's see here. This is approximately the cubed, x cubed. If we want to see a better one, I can x to the 3rd graph. We have this here, so it does kind of look like our graph. that we have. But again, if we're saying plus 2, we're moving the whole function where? Up 2 units. And that's it. We're moving the y value up 2 or moving it down. When we add or subtract something outside of the function, so the absolute value function minus 3, or x cubed plus 2, we're applying that transformation to the y values. Even if we're just given points and not a function, we add something to it, we're just moving the y values up or down. If we look at the graphing calculator, so we have x cubed there, x cubed plus 2, graph. If you notice that every single y value just got moved up 2. If we look at the table, at 0, 0, because at 0, the first one was 0. Now it is at 2. When x is 1, it was originally at 1. Now it is at 3. That's all we're doing. If we'd done the same thing with x cubed, but said minus 2, if we just move it down 2. So at 0, 0, when it was 0, 0, it's now at 0, negative 2. We're just moving the y values either up or down. And that's it. Questions on this here? And if we were wanting to graph this in Alex, all you got to do is pick our center point. So for just x cubed, we'd pick 0, 0 and plot it, then 1, 1, 2, 8. Or negative 1, negative 1, negative 2, negative 8. Dot the graph, and it is finished. Questions on these here? Now, inside the parentheses, I probably put these in the wrong order. Let's see here. Yep, okay. I'm missing the note with this, so that's fine. F of x minus h. Whatever's inside the parentheses moves it to the left or to the right, moving it left or right. And most parent functions for any of these here start at 0, 0, and we're moving it accordingly. Now, x plus 3, now the movement's always opposite of what we think, because x plus 3 looks like it should move it 3 units to the right, but it's going to move it 3 units to the left. Because what it's really saying, or if we really wanted to look at it, is x minus negative 3 squared. But the general form of the movement is x minus h. So to get that subtraction, a positive is really just saying we're subtracting a negative. So what that tells us also is that our vertex is at 3, because the vertex for any quadratic is at the point 0, 0. It starts at 0, 0, and we can move it left, right, up, down that amount. So here it says it moves it 3 units to the left. So our vertex is at negative 3. Now, did we move the function up and down at all? Well, no, there's nothing added or subtracted outside. So the vertex started out at 0, 0, yes? Moved it 3 units to the left, so x is now negative 3. And if we plug this in, negative 3 plus 3 squared to get the y value. Negative 3 plus 3 is 0, 0 squared is still 0. So the vertex still has a 0 for the y value. Negative 3, 0. Now at this point we need 2 units or 2 spots to the right, 2 spots to the left. Now at this point here, if you wanted to plug x plus 3 squared in the graphing calculator and let it generate the points, that's fine. Or we could plug it into the function negative 2 plus 3 squared. And you can plug that in a calculator. Parentheses, -2 plus 3, close parentheses squared. But if we did it by hand, -2 plus 3 is not -1, is 1, and 1 squared is 1. We can do the same thing with -4. -4 plus 3 would be -1 squared, which is 1. And as we see here, the y values to either side of that are the same. Now, we can move on to -1. So -1 plus 3 squared is 2 squared, which is 4. And lastly, -5 plus 3 squared is -2 squared, which is, interestingly enough, 4. Now in the ALEKS program, we can plot it: -5, 4, -4, 1, -2, 1, -1, 4. And that would give us our quadratic. And that's it. Graphing calculator gave us the exact same thing. So we get the vertex, -3, 0, and go 2 spots to the left and right. Questions on this here? Use the translation to graph the function. Now, this here is the parent function. This is the square root of x function. And if we wanted to deal with the transformations of it, we look at the function. Now, what's inside the parentheses on the last one? Moved it left or right. What's inside the square root for the square root functions moves it to the left or to the right. Since it's the square root of x minus 3, it makes it look like this function is going to move where? It looks like it should move to the left, yes? Which way is it actually going to move? To the right. How far? Three units. Is our original point where it starts is at 0, 0, yes? But what's going to make x minus 3 be 0? Positive 3, because 3 minus 3 is 0. Any questions on the first movement? Now the -2 out front tells us it's going to move where? From there. Down 2. So you take it and move it 1, 2. And that there's our new function. Questions on this here? Not too bad. Now the other way we can graph it, because again I said whenever we look at radicals, we really want to see what's going to make inside the radical, whatever's inside the radical, be 0, because that's going to give us our starting point. So I can set x minus 3 to 0, plus 3, plus 3. So x is 3. So one of our starting x values we know is going to be 3. As long as x is positive, we pick values bigger than it. If x is negative, if we had negative x, then it's going to be smaller. But here, since x is positive, we're going to start out with 3. Then we could do 4, 5, 6. Most likely, not all of these are going to be nice. 4 will. And plug it in, because we can say the square root of 3 minus 3 minus 2. Square root of 3 minus 3 is 0. Square root of 0 is 0. And 0 minus 2 is negative 2. Isn't that our first point? Well, yes. Then we do the same thing with 4. We do square root of 4 minus 3 minus 2. Well, 4 minus 3 is 1. Square root of 1 is 1. And 1 minus 2 is negative 1. Where negative 1 is the point we have on the graph, yes? Does it look like 5 is going to work out nicely? Probably not. It looks like it on the graph that we have. Square root of 5 minus 3 minus 2. 5 minus 3 is 2. Can we take the square root of 2 and get a nice number? No. Square root of 2 is irrational. Now for the program Alex, you can plot the point 5 comma square root of 2 minus 2, and it'll give you the point, which is somewhere about right here. Now, I'm going to skip 6 and say 7, because we can see here on the graph 7 does look like it's going to be a nice number, and we can check it. 7 minus 3 minus 2. 7 minus 3 is 4. Square root of 4 is 2, and 2 minus 2 is 0. We got those points. Plot them in Alex, hit our graph function, and you have the graph. Questions on this here? We feel good with this here. Vertical stretch and vertical shrink. Let's just say that the y values are going to increase faster or slower by set amount. Now the graphing calculator will help you with a lot of these. That there is the absolute value of x. The lowest point we see is 0, 0, so we can start at the origin and go left and right. Because the left, negative 1, 1. Right, 1, 1. And we have this here. Now 2 times the absolute value means that the y values are going to increase by a factor of 2. So we can say 2 math over absolute value of x graph. It's increasing faster. It's going up faster. And we go second table. Still, the smallest y value that we have is 0, and it's at 0, 0, so we're still at the origin. But this time, when we go to x is 1, the y value is not at 1, it's now at 2. We essentially took the y value, whatever it was, and multiplied it by 2. So even if we're given a point, and they tell us that the y value has a vertical stretch of 2 times the function, it means we're taking all the y values and multiplying them by 2. 2, 4, 6, 8, 2, 4. So it's increasing by a factor of 2 faster. for the second one. And the last one, 1/2. What do we think all the y values are going to be now? Half of what the original value was. Alpha y equals enter 1/2 math over absolute value of x. Graph. Now the y values are half the original amount. So if the original one was 1, it's now at 1/2. So 0. 4 is now at 2. At 4. So if we're given the points and told it 1/2 times the function, we just take whatever the y values are of said function and multiply them by 1/2. Questions on this here? Not too bad. We good? Now, I mean, even if we had points, this is, and I was just plotting here, here, and let's say here. And I told you this is the function, and we'll look at some of these later. And we're taking half of it. We're just saying the y values are multiplied by 1/2. So at -3, the y value is 4. It's now at 2. At 0, 0, it's still going to be 0, 0. Because if we take half of 0, it's still 0. And over here at 4, the y value was at 2, but half of it's now 1. So that's half of that function. Even though we don't have a function itself, we can still take half of it. We can also double it. Because the original point, the y value is at 4. We double it, it's now going to be at 8. Here, the original y value is at 2. If I double it, it's now at 4. But interestingly enough, 0 is still 0, no matter what we do to it. So that's our new function. And we do have this here. It would have been nice if I probably had those flipped. Vertical stretch, if a is greater than 1, it's a stretch of that amount. If a is between 0 and 1, it's a shrink by that amount. Horizontal, this one's the one that is always going to be tricky. Because whatever the value of a is, you have to flip it. If they tell us that it's 2x, inside the parentheses, we're actually affecting all the x values, not by 2, but 1/2. It's always a flip of whatever it is. If they tell us that the a value is 1/2, it's actually factoring it by a factor of 2. So if this is 2, it's affected it by 1/2. These are funky, these are weird. So it's always a flip of whatever you think it is. And it's kind of the same with vertical stretch, vertical shrink, because inside 2x, 2 times x inside the parentheses, looks like it should be a stretch of 2, but it's actually a shrink of 1/2. When it's 1/2 times x inside the parentheses, it looks like it should be a shrink of 1/2, but it's actually a stretch of 2. And that's what this is talking about here. It didn't give us an actual function. But this is horizontal stretch and shrink for both of these here. We'll do red for the first one. Because if we're looking at this here, so it's 2 inside the parentheses, but we're not affecting the x, because again, inside the parentheses is affecting the x values by a factor of 1/2. Now our first point here, we have -4, -2. Here's one of our points. Our next one is at -2, 4. And our last one is at 2, -2. These are our 3 points they were given to us. but we're affecting the x value. We're multiplying it by 1/2. So what we're saying is here, we're taking -4, multiplying it by 1/2. Well, -4 times 1/2 is -2, -2. That's our new point for this here. We'll do the same thing with -2, 4. Well, -2 times 1/2 is -1. That shouldn't be 2. That should be 4. So -1, 4. And if you notice for these 3 points so far, the 2 points so far, the y value is not changing. We're only affecting the x. And the last one. We'll do 2 times 1/2, which is 1, and we still have -2. Questions on how we got these 3 points? We good with this here so far? Yes? Now, in the function, or in Alex, you'll use the line segment to connect those two. Use the line segment again to connect those two, and that's your graph. So you can say that this is A, B. Now we have 1/2 x, which means we're affecting this function by 2. We flip it. So 2 flipped is 1/2. 1/2 flipped is 2, which means each one of these, we're multiplying the x value by 2. So -4 times 2 is going to be -8. So we have -8, -2. -2 times -2 is -4, 4. -4, 4. 2 times 2 is 4, -2. And this here is our new function. And if we notice, the one in green has been expanded along the x-axis. It's been stretched along the x, where the one in red has been shrunken along the x. Any questions on either one of these here? We're okay with these here? Yes? And the last one that we have here is we're multiplying it out in front. Now again, inside is affecting x. The numbers outside are going to affect the y values. Anything added to it will affect the y up and down. Inside the parentheses is x. So here, we're multiplying, so we're taking all of our points, and we're going to multiply the y value by 2. which means our first one here is going to be negative 4, because negative 2 times 2 is negative 4. Our next one, negative 2, well, 4 times 2 is 8. And lastly, we'll have 2, negative 4. And we can just plot these here, negative 4, negative 4. Negative 2, well, 8 is going to be up there. And lastly, 2, negative 4. And we get this here. Questions on any of this here? Well,